For almost 100 years, our entire picture of the cosmos has been built on this one really beautiful and simple idea. But what happens when we start finding things that just don't fit? Today, we're going to dive into some mind-bending evidence that suggests our universe might not be the nice, orderly place we've always imagined.
So, where do we even start? Well, to understand why these new discoveries are so shocking, we first have to get a handle on this foundational rule. It's an idea that underpins basically everything we think we know about the cosmos. I love this quote from astronomer William Keel. It just perfectly captures the spirit of the whole thing. It's this core belief that the universe isn't trying to trick us. This idea is called the cosmological principle, and it's basically the assumption that what we see from our little perch here on Earth is a fair sample of, well, everywhere else. So what does that mean, really? Imagine you could zoom way, way out from our galaxy. So far out that entire clusters of galaxies look like tiny specks. The cosmological principle says that once you're zoomed out that far, the universe should look totally uniform. All the lumpy bits, the stars, galaxies, the voids, they should all just average out into this smooth, consistent cosmic soup. No special spots, no weird edges. Okay, so this principle really boils down to two key ideas that we can actually test. First, there's homogeneity. That just means your location doesn't matter. If you could teleport to a galaxy billions of light years away, your neighborhood should look pretty much the same as ours. The other idea is isotropy. That means the direction you're looking doesn't matter. It's the same view north, south, east, or west. And you really need both for the principle to hold up. So why is this idea so important to physicists? I mean, yeah, it makes the math a lot cleaner, but it's so much deeper than that. It turns out this principle is woven into the very fabric of physical law through this absolutely beautiful idea called Noether's theorem. Seriously, Noether's theorem is one of the most elegant things in all of science. It's like a cosmic love story. Wherever you find a symmetry in the universe, you are guaranteed to find something that is conserved. One literally cannot exist without the other. And this is where you see just how high the stakes are. The idea that the laws of physics are the same today as they were yesterday, that symmetry gives us the law of conservation of energy. The universe's homogeneity, the fact that it's the same everywhere, that gives us conservation of linear momentum. And anisotropy, that it's the same in all directions, gives us conservation of angular momentum. So the cosmological principle isn't just a nice thought, it's the bedrock that guarantees these fundamental laws work everywhere. Okay, so we've got this beautiful symmetric picture. But what if it's wrong? What if the universe isn't smooth at all? Let's look at how the first giant cracks in this idea started to show up, beginning with a major challenge to homogeneity. According to our best models, there's a kind of line in the sand. Once you get to scales of about 250 million light years, the universe is supposed to smooth out. All the clumps and empty spaces should just average out, and everything should look statistically the same. Well, when we actually started mapping the universe on these enormous scales, we found things that just shouldn't be there. We found structures so unbelievably massive that they completely break that 250 million light-year rule.
And we're not talking about just a few extra galaxies here. We're talking about cosmic walls and filaments of galaxies that stretch for billions of light years. The Sloan Great Wall, the huge LQG, the giant arc. With every new survey of the sky, the list of these impossible structures just keeps growing.
And then there's this monster, the Hercules Corona Borealis Great Wall. It's estimated to be 10 billion light-years across. That's almost a tenth of the size of the entire observable universe. That's not just a wrinkle on a smooth canvas. That's a giant gaping tear in the fabric of homogeneity. So a lumpy universe is a huge problem. But there's another challenge that might be even more profound. This one takes aim at isotropy, the idea that the universe looks the same in all directions. And it doesn't just question where the matter is, it questions the laws of physics themselves. So, some scientists had this wild idea. They looked at light from incredibly distant quasars to check on one of the fundamental numbers of nature, something called the fine structure constant. You can think of it as the master dial that controls the strength of electromagnetism. The big question was, has that dial always been set to the same value, everywhere and for all time? And here's where it gets really weird. A team using the Keck telescope in Hawaii looked in one direction of the sky and found that billions of years ago, the constant seemed to be just a tiny bit smaller. But then, a totally different team using the Very Large Telescope in Chile looked in the opposite direction, and they found the exact opposite. The constant seemed to be a tiny bit larger. Put it all together, and you get this bizarre pattern. It's called a dipole. It's as if the universe has a preferred axis, a sort of north and south pole, where the laws of physics literally change. This would be an incredible violation of isotropy. It would mean the rules of the universe depend on which way you're facing.
Now, in science, you have to talk about how certain you are, and the statistical significance of this result is 4.2 sigma. To claim a discovery in physics, you usually want 5 sigma. But let me tell you, 4.2 is the kind of number that makes scientists sit up and pay very, very close attention. It's way beyond a random fluke.
So what's the bottom line here? It's a hugely significant finding. The data seems solid, but science has a really high bar for a reason. Before we go and rewrite 100 years of cosmology, we need more telescopes to look, more data, and more checks to make sure we're not being fooled.
Okay, let's just step back and take a breath. We've got these colossal structures that seem to violate homogeneity. And then we have a fundamental constant of nature that seems to change based on which direction you look, violating isotropy. So, where does that leave us?
Well, it's a direct assault on our best picture of the universe, the lambda CDM model. That model has been incredibly successful, but it's built entirely on the foundation of the cosmological principle. If that foundation is cracked, the whole building might be unstable. It could force us to rethink everything.
You know, this is exactly the kind of stuff that gets physicists excited. These aren't failures, they're clues. They might be breadcrumbs leading us to a much deeper, more complete understanding of how reality actually works, a new physics that can explain why the universe seems to be lopsided. And that really leaves us with this one final huge question. If the universe isn't the same everywhere, if it has special places and preferred directions, what does that mean about our own place in it? It's a challenge to some of our oldest assumptions, and honestly, it's opening up one of the most exciting new frontiers in science.